So good afternoon, everybody. We are going to be doing a little bit of applied math here to a very, very serious topic, and that would be the chemistry of flatulence. Now, before we get started, I do want to pull up and let you watch a couple things just to kind of get in the spirit of stuff here. So give me a moment. Share. We're going to share this one here. Nice for video and share.
I can't believe it. It's my first blind date.
Oh, I do it all the time.
Really? Whew. You guys meet? Greg, Janice?
We sure did.
Great. We've got chemistry here. You feel it?
I felt it.
All right, Janice.
Here he goes. Maybe.
Well, it's true that I fart, but I wouldn't call myself a farter. I'm a social farter. I really only do it when I'm out with my friends that fart. We hang out, we drink, we dance, just have some fun being together. Farting. Sometimes I'll use farting as an excuse to meet a guy. Do you want to go outside for a fart? We talk. We fart. Just because I fart at parties now and then, it doesn't make me a farter.
So there you go. So we are going to be talking about the chemistry of farts. We're going to be talking about flatulence, and we're going to be making it as boring as possible, of course, by making it all about math. So let's take a look at this paper here, and let's do a little bit of reading and a little bit of writing and a little bit of mathing. Methane. You already know methane, CH4, is the main component of natural gas. Natural gas is a popular fuel for generating electricity in power plants and heating homes. It's also used for your gas stove if you have one of those. It's used for your water heater. It is very clean burning. When you burn it, it only makes carbon dioxide and water vapor. Methane is also made in the human gut during digestion. So as it passes through your digestive tract, it collects down in the lower end of things, and it gets let out as something called a flatus. Flatus is the sciencey name for a fart. And of course, the hydrogen and the methane in fart gas is flammable. About 10% of any given fart is made of methane. There's a bunch of other stuff inside there. However, it's not the methane that gives farts a bad smell. There's another gas inside there called hydrogen sulfide. It's the same odor you get when you have rotten eggs. And so, you know, everybody does it. It's nothing to be ashamed of. It's one of the funnier things about being a human being, in my opinion. But the important bit we're going to start with here is this fact that the average human fart contains about 0.00643 grams of methane gas. So we're going to start out by writing and balancing a reaction for combusting methane. I'll do part of that for you. I will write it, but I will leave it up to you to balance it. So we're going to start out with methane, CH4. Anytime you combust something, remember what you're doing is you're combining it with oxygen gas. In combustion reactions, your products are always carbon dioxide and water vapor, H2O. So that's your unbalanced equation. I will leave it up to you to balance that. So don't forget to balance that later on. Actually, we're going to have to balance it before we go on to number 2. Ah, darn it. Okay, fine. So just remember how we balance things. We draw our line. We make our scoreboards. On the left-hand side, I've got 1, 4, and 2. On the right-hand side, I've got 1, 2, and 3. So I'm going to start by trying to fix my hydrogens by doubling this here, which is going to give me 4 hydrogens. It's going to give me a total of 4 oxygens. And I can fix my oxygen very simply by putting a 2 right here, and I'm balanced. Okay, fine, that's a freebie. Let's look at number 2. If you are too light, said fart, and you should not, it is seriously dangerous. What mass of oxygen would combust along with it? So we are looking for mass of oxygen. So oxygen here is going to be our B. We are starting with our methane, which is going to be our substance A. Now it says right here that every fart contains that many grams of methane gas. So we're going to set this up. We're going from grams of A to grams of B. So if you had your football, you would be using your full football to set this up. We start out with what we're given, which is the 0.00643 grams of CH4. I'm going to put that over 1. In our next step, we want to change from grams into moles, so we're going to go 1 mole CH4 on top. Now we need to find the mole mass of CH4 for the bottom. You can either do that with periodic table, or if you will do a little bit of Googling, and if you will Google the phrase molar mass calculator, like I've done right here, it will give you about 1 million different web links you can click on. Just pick one you like. I liked this one here. I'm going to come down here where it says chemical formula, and I'm going to type it in using capital letters for my C and my H. CH4. Oh, it already knows it's methane. When I click calculate, it tells me that the total molar mass of the total molecular weight is 16.04 grams. I'm going to go ahead and just round that to 16 to keep my math simple. I'm going to say 16 grams of CH4. In this step, we look at our mole ratio. We have moles of B over moles of A. So I'm going to have 2 moles of O2 on top, 1 mole of CH4 on the bottom. Oops, mole, my bad. And in the very last step, we want to go 1 mole of O2 on the bottom, and we want to find the mole mass of oxygen in grams to put it on the top. So let's just come in here and let's go O2, hit enter. 32 grams, easy enough. Now remember, when you set up a stoichiometry problem like this, you can cancel units, so grams of CH4, moles of CH4, moles of O2. What I'm left with is grams of O2, which is what it wants me to find. You're then going to multiply everything on the top, divide by everything on the bottom, and just to make it fun, I'm not going to tell you the answer to that one, but I will tell you on your calculator, you're going to take that number times 2 times 32 divided by 16. Let's look at problem 3. People pass on average, wow, 3/4 of a liter of gas a day. That's going to be about 0.0536 grams of methane for every 24-hour period, because only 10% of farts are methane. So what mass of water could be generated by ignition of these methane emissions for 1 person? So this time, we're trying to look and see how much water is going to get made if you were to capture and light all the methane in 1 day's worth of farts. So we're looking this time We're making this B. And again, we're going to leave this as A. And so setting up our problem down here, it's going to be in a lot of the same way, except we're going to start with this new mass for methane. So 0.0536 grams. Nice thing is, since we looked up some of this stuff in the last problem, we don't have to look it back up again. Or you know that 1 mole of CH4 is going to have a mass of 16 grams. For our mole ratio this time, we've got B and A, so our mole ratio is still going to be 2 to 1. Oh, you can't see that. Still going to be 2 moles of this for every 1 mole of this. So we put 2 moles of water on top of 1 mole CH4. And we need the mole mass of water. So again, I'm going to cheat, and I'm going to look it up on here. I could just pick it off a list. Wow, that's a long list. I'm just going to type in H2O. About 18 grams. So let's see. 18 grams H2O over 1 mole H2O. Again, you cancel your units. So it's going to be 0.0536 times 2 times 18 divided by 16. It says that my internet connection is unstable. So again, I'm videoing this. If you're not able to get a good connection, I will have it up in video later, so don't panic. And then that's going to give you your answer. Again, I'm not going to do it for you. I do want to look at number 4, because number 4 says how many water molecules is this? So to find the answer to that, you're going to do exactly what you did in this part right here, except you're going to want to leave this last step off right here, because if you leave off that last step, then you're going to end up with moles of water. Now to get water molecules, you're going to take whatever your answer is at that point. So let me bracket all that, times Avogadro's number, which is 6.02 times 10 to the 23rd. And that will give you water molecules. And hey, we're halfway done. Or at least we're through the first page. Let's come back out and look at page 2. Okay, problem's bigger than this, because if you're talking pound for pound, who is doing the most farting on planet Earth, we're talking about cows and other ruminant animals like sheep and goats, because they are eating lots and lots of grass that they have a hard time digesting, and they make a lot of methane. It says that a study of methane emissions in '95 found that cows typically lose about 6% of their ingested energy as methane, and a single cow can produce between 250 and 500 liters of methane a day. Folks, that's an awful lot of unburned energy. Imagine if we had some way of harvesting all of those cow farts and turning them into clean burnable energy. It would be ridiculous. But as it is, that methane just gets right out into the atmosphere, okay, where it's not doing anybody any good. So it wants us to know here what mass of methane does a single cow produce, and I'm going to go per day. So it wants us to calculate the high and the low end. So we're going to be starting with 250 and 500 liters of methane a day. Now, fortunately, we learned yesterday that for any given gas, 1 mole of a gas at STP is equal to 22.4 liters. Remember that? So what we can do is we can start off with a quantity of gas. And so we're going to be starting, let's start with the low end. We're going to start with 250 liters. So 250 liters of CH4. Now we know that 1 mole of CH4 is equal to 22.4 liters of CH4. And so at that point, we would have moles. And if we want to change it into grams, we know that 1 mole of CH4, looking back at our prior paper, is about 16 grams. So at this point, liters cancels liters, moles cancels moles, and you're left with grams. So it's 250 times 16 divided by 22.4. Now that right there is going to give you the low answer. It also wants to know what it is on the high end. Well, if the high end is 500 liters, that's twice as much, right? So then you take this times 2 to get the answer for the high end. Easy, right? For problem 6, it says we have about 39 million beef and dairy cattle in the U.S., so what mass of methane would this be per year? So what we're going to have to do is you're going to have to take one of these two answers. Now one of these two answers right here is per day for 1 cow. Okay? So you're going to have to find some way, if it's this much per day at the low end, you're going to have to figure out, okay, well, how much would it be for this many cattle per year? So you take one of these answers, you have to figure out a way to inflate it, if you pardon the expression. Instead of 1 day, how many days are in a year again? 365 is what I hear you thinking, but do you know it's actually 1 year? If you're doing this kind of math, it's 365.25 days. Think about why that is. And then, of course, you're going to have to change it instead of 1 cattle. I'm not sure that's how you say that. Instead of 1 walking burger bag. You're going to have to do it for 39 million of them. And after you get that answer, if you use the low end number, you're going to want to go times 2 and do it for the high end number as well. I'm going to leave all of that to you. But let's take a look at the very last problem here. Finally, on January 28th, 2014 in Germany, a barn containing 90 cows exploded when a stray spark caught the methane trapped in the building on fire. Whew. The building was damaged and 1 cow was slightly injured with minor burns. Okay, just, rare. Assume that the 90 cows are producing 250 liters of methane per day and that there was a 15-hour collection in the barn when it ignited. Now, this 250 liters is per cow. Very important. And there is a 15-hour collection. So that's per cow per day, but if it was not an entire day, then you're going to have to figure out some way of it only being 15/24 of a day. Or maybe you can get the total amount and go 15/24 of that amount per cow, multiply it times the 90 cows, and that's going to get you the starting mass of methane, okay? So once you get the starting mass of methane, it's going to be in grams of CH4, then it wants to know what mass of water was generated. So fortunately, we can go back and we can steal some of our math from the previous page, particularly this part right here. We can take this step, and this step. So it's going to be 1 mole CH4 over 16 grams CH4 times 2 moles of water for every 1 mole of methane times 18 grams of water for every mole of water. After you find all that, that's going to get you the answer in grams of how much water vapor theoretically could be made in that one massive barn full of cow fart explosion that burned the German barn down. And with that, dear students, I am going to bring us to the end of this recording. After I click stop, if any of you have any questions, you can stick around and ask. Otherwise, wish you all the best of luck.